All right, for our summer calculus practice, you're asked to find the derivative of each of our functions in terms of t. So t is the variable that we're going to be looking at. When it comes to determine the slope of the function when time equals 5 seconds, that's exactly what a derivative is. What you're finding when you do a derivative is you're finding either a number or a function that will define what the slope is. So basically, for numbers 1 through 6, once we complete the first part of solving for the derivative, we simply add in t equals 5 into our equation, and we solve. So it is as simple as that. So what we'll be doing here is we'll be doing the power rule. So the power rule tells us that we're going to take the exponent that we have for our variable, so in this case it's a 2, and we're going to multiply that by our coefficient out front, and then we drop the exponent by a value of 1. So I end up with 2 multiplied by 3 gives me a 6. I keep the variable t. The exponent of 2 drops down to an exponent of 1, so I have 6t to the first power, plus this right here is t to the first power, so 4 times 1 is just a 4, and then t drops down to a power of 0 because 1 minus 1 is 0. And then last, I have 7t to the 0 power, technically is what I have, so 0 times 7 gives me 0. If I clean this up a little bit, 6t to the first power is more commonly referred to as 6t. T to the 0 power is just a 1, so I end up with 4. And then plus 0, obviously I don't need to write that out. So my answer for the derivative is going to be 6t plus 4. If I put t equals 5, I end up with 6 times 5, which is 30, plus 4 for a total of 34. So at t equals 5, our slope is going to be a value of 34. Question number 2. Same thing, so I have my exponent of 3, so negative 6 times 3 gives me negative 18, t to the second power, because I dropped the exponent by 1. This right here, 20, t to the 0, t to the first, this is t to the 0 power, 20 times 0 gives me 0, and so my function for the derivative is going to be negative 18 times t squared. So if I plug in the number 5, I end up with negative 18 times 5 squared, or negative 18 times 25. That gives us an answer of negative 450. Question number 3, I have 12t to the first power. So 12 times 1 is 12. T to the 0 power. T to the 0 power is 1. So our answer is simply 12. When time is equal to 5, there is no time in this function, which means that at 5 seconds, it's 12. It's always 12 at any time at all. Over here, 100. I can put t to the 0 power because that's a 1. 100 times 0 is 0. So in this case, my slope is going to be a value of 0, and it is always going to be a value of 0. So it will not change. Our slope will remain 0 the entire time. If you think about what this looks like, y equals 100, that's just a line that's going to be staying, a horizontal line that's at 100. So a slope of 0 makes perfect sense. Now, as soon as you get into number 5 and 6, where things start to look a little bit different, my suggestion would be express it in terms of a standard exponent. Instead of 48 divided by t, I can think of this as 48 times t to the negative first power. Now I just follow the same rules as before. So 48 times the exponent of negative 1 gives me negative 48. I take my t, the negative first power. If I subtract the number 1 from that, I get negative 2. Technically, you could leave it just like that. If you want to put it into a different form, you could go negative 48 divided by t squared. whichever one works. To find our answer, 48 divided by t squared, so t is still 5, so 48 divided by 5, which is just about a value of -2 or so. Question number 6, we have this radical. So again, thinking about what that radical, what that means and how I can express that in terms of an exponent. So what I have here is, now obviously having the square root of 4 is convenient, but if it wasn't a convenient number, I could leave this as the square root of 4, and then I can take my t. A radical is going to be to the 1/2 power. Now, because the square root of 4 is a convenient number, might as well write it out as such. So I have 2t to the -1/2 power. Now that I have a number for my exponent, I do the same thing as before. So 2 times 1/2 gives me a value of 1t. I take my 1/2 exponent, subtracting the number 1 gives me a -1/2 exponent. So I end up with t to the -1/2 power. I can express that if I'd like. I can express that as, oops, my marker has all of a sudden gone. All right. So I can express that. Okay, great. My marker's not working out. So t to the -1/2 power, so I could have that as 1 over the square root of t, however you want to do that. Plug in the number 5 and I get my answer. Coming down here, will the slope of the function from above ever be 0? So these 3 questions are actually things we've already done up here, so that just saves us some work. You've done 6 questions of practice up here, so now I can just apply that. Will the slope of the function from above ever be 0? Well, the slope is our derivative. We solve for the derivative. Question number 1 is the same as question number 7, and so I have 6t plus 4. So I have 6t plus 4. That is how we express. That's how we express our slope. So if the question is, will it ever be 0? Well, can I put in an equals 0? If the answer is yes, then yeah, it will, and then we can solve. So I end up with 6t plus 4 equals 0. So if I subtract my 4 over and then divide over my 6, I end up with -2/3 or -0.7 roughly. So at -0.7 t, that is when we'll have a slope value of 0. Question number 8 is the same as question number 3. So if I just pull down my answer, 12. Can I do this? The answer is no. So 12 cannot equal 0. So will it ever be 0? No, it will not be 0. And last question number 9 is question number 4. So we have an answer of 0. So I come down here. Our slope is 0. So the question says, will it ever be 0? Yes, it will be 0 always, because we have a horizontal line. When I come down to the end here, graph the derivative of each function below. So remember, the derivative equals the slope. So basically what I'm trying to do is I'm trying to make a graph that shows the slope. So right here I have a negative slope, and it is large. Right here I have a 0 slope. Right here I have a positive slope, and it is large as well. So I go from a large negative value to a 0 value to a positive value. So coming down here, large negative, 0, positive, I end up with this nice simple straight line going up. For the next one, looking at my slope here, my slope, I have a large negative slope. I have a small positive slope. Where the graph falls doesn't matter. So the fact that I have positive values up here and negative values down here, that doesn't matter. All we look at is the slope. So I have a big negative slope, a small positive slope, and a 0 slope. So what I'm going to do is I am going to add in some lines here. So I'll put this little vertical line here. I'll put this vertical line here. This allows me to see where on my bottom graph these things are occurring. So I need a large constant negative slope. So that means when I come down here, I'm going to need to have a big negative value, line got a little crazy there from the board. Let's try that again. So a large negative value until I get to that dotted line there. Didn't quite reach all the way down. Then I have a constant positive small value, something like that. And then we have a horizontal line which has a 0 slope, something like that. And last, regardless of where the graph occurs, I'm looking at the slope. I have a large positive slope here, and that slope is slowly becoming a 0 value. So I have to have a positive at this location, a positive value that drops down and starts to approach 0. So here is a positive value from my slope, and eventually it approaches 0, so something like that. Not the straightest line, but we get the idea.